Solving the quantum encryption threat using quantum. I'm Tonya Hall, and joining me is Dr. Shohini Ghose, professor of physics at Wilfred Laurier University and founding director at the Center for Women in Science at Laurier. Welcome, Dr. Ghose.
Thank you.
So, give us a brief summary of your physics background as it relates to quantum computing.
Yeah, so I'm in quantum physics. My training is in physics in general, so my PhD is in the area of physics. And my focus is in the area of quantum computing, which is relatively new, but also old because it's based on quantum theory, which has been around for over a century now. What's new about it is applying this old theory to new kinds of tasks such as computing, communication, security questions, and who knows, maybe tasks that we haven't even, figured out as yet. So that's basically what I focus on. And my other area of research more recently has been also on gender issues and identity in science.
What is the foundation of data encryption today, and why does it work so well in a world of classical binary computers?
Yeah, so data encryption has evolved actually a lot over the years. So back in the old days, we would encrypt using mechanical systems, or we would use some very simple kind of, almost like children's codes, right? Where you replace one letter of your message with another letter, and only you know the secret and others try to figure it out. And this was all very safe and good for encryption before computers existed. But computers can search through those kinds of encryption methods very easily and crack them. So now what's done is to try to figure out much harder problems that even computers that exist today find really hard to solve. So one of these problems, which we know is a very hard problem, even with supercomputers, is factoring of large numbers, believe it or not. And so this is actually what's used as a basis for encryption. So for example, if a hacker tried to hack your passwords, for example, they'd have to know how to factor very large numbers because the encryption is based on that. And if they don't have access to, supercomputing, they probably will not be able to do it. So that keeps all of us safe today. But of course, computers are getting better and better all the time and more powerful. So something that is not easy to solve today may not be that hard tomorrow. So basing encryption on mathematically hard or computationally hard problems is not completely fail-safe. So the reason we're okay today is because computationally our computers are not able to solve these very hard problems, but that could change in the future.
So how do quantum computers threaten today's encryption methods?
Well, quantum computers are a kind of a computer that operates very differently from our current computers. So this is not just one more, generation of new computer chip from Intel or Apple or anything like that. This is a whole different technology. So it's like going from driving cars to, having spaceships, right? So if we have that kind of computing technology, then current encryption problems, which, as I mentioned, are based on having certain limits to computing power, no longer are within those limits. So a quantum computer could be able to crack problems like factoring in minutes. So everybody's private information becomes open. It's a real threat.
So can we solve the quantum threat using quantum?
Yes, luckily for us, now that we're realizing that quantum computing is perhaps on the horizon and can really threaten what we have today, we have to think about what else can we do. So there are different ways actually to protect. We could say, well, let's not go with factoring or that type of problem anymore. Let's find a whole new type of mathematical problem that even quantum computers would find hard. And this is definitely what is being done today as an interim measure, I would say, meaning, again, we don't know, even if we find such problems, we know of a few. Maybe in the future, somebody will figure out a way to hack those kinds of problems as well. So going with math problems is perhaps good for now, even if we go with different problems. But in the future, what would be wonderful is if you could really have an encryption system that could not ever be hacked, no matter how much computing power you have. So something that is not about computational power in the first place. Turns out quantum gives us that kind of an option. And that's because we can actually build encryption by encoding information in quantum objects in such a way that to hack the information and steal it, you'd have to break the laws of quantum physics itself. And I don't think anybody expects that to happen just by having better and better computers. So this is a way of approaching encryption in an entirely new sort of way, which is to not even think about math problems or computation, but embed encryption in the laws of the universe. So it's very exciting and amazing that it's possible. It's now a question of how much time it would take to build such an quantum encrypted, let's say, internet, for example, or system of encryption.
Well, and I think that the big question then is, I think for a lot of people that are, this is a scary idea. How long will it be before the data encryption that individuals and businesses rely on become compromised? And will quantum encryption be ready in time?
Yeah, this is the million-dollar question. So, anybody who tries to predict the future of technology always gets it wrong, right? So, for example, we all thought we would have flying cars by now. And boy, we were wrong. So I don't know if I can predict for you very accurately when the technology will come online and when we can change over. What we do know is that in the past, transferring or converting all of our encryption standards to what's being currently used takes a lot of time. Think about it. Now we have so much information, so many database systems all around the world. You can imagine that this is a huge amount of infrastructure and communication that has to be developed in order to change all of the standards and also build the hardware combined with the new software to change all of our encryption. So we're talking about a change that will already take us maybe decades. Now, quantum computer may not be just around the corner in the next year, but even if it's maybe decades away, we need to start changing and updating and getting to a new system now because it'll take us that long to change. And another reason we need to change is that if there are, let's say, hackers today who are just, have found a way to not necessarily read our information, but a way to store the information. Maybe they can secretly access the information and then store it in encrypted form today and wait until a quantum computer is built that they can access and then use it to hack the information at that time. There's lots of information today that will be relevant even, let's say, in 20 years, 30 years, all of our, let's say, health data, personal data, financial data, those are not just about being kept safe today, but also in the future. So we have to really start thinking about these and making our updates and moving away from current encryption today.
Dr. Shohini Ghose, professor of physics at Wilfred Laurier University and founding director at the Center for Women in Science at Laurier. Thanks again for joining us, Dr. Ghose. If somebody wants to connect with you, how can they do that?
I'm actually very easy to find online. If you do a search for me, you'll probably get to my website. Or if you go to the university website, which is very easy to remember, it's wlu.ca, and do a search in the physics department, you will find me.
Thanks again for joining us. And if you guys want to find more of my interviews, you can do that right here or go to tonyahall.net. Thanks for watching.